Hey physics students, this is Scott from PengPrep.com. Welcome to video 1.2, the 5 kinematic equations. There are 5 variables associated with motion: displacement, initial velocity, final velocity, acceleration, and time. And there are 5 equations which relate these 5 variables. We call these the 5 kinematic equations. The reason why these equations are so important is because if you know 3 of the 5 variables, you can always find for an unknown variable by using one of these equations. In this video, you'll learn how to prove these equations and apply them to problems. And although it's unfortunate, you'll eventually need to memorize all of them. The first equation is final velocity equals to initial velocity plus acceleration times time. And the proof is pretty intuitive. Acceleration is how much an object's velocity changes per second. So if the object starts at an initial velocity of vi and gains a velocity of a meters per second every second, then after t seconds, it has gained the velocity of at meters per second. And so its final velocity is going to be the starting velocity, vi, plus how much velocity it gained, at. So vf equals to vi plus at. For example, if an object begins at 3 meters per second and accelerates at 2 meters per second squared for 4 seconds, then it gains 2 times 4 equals to 8 meters per second. So its final velocity is 3 plus 8, which is 11 meters per second. Before we move on to the next question, you should be familiar with the letters which represent the 5 variables of motion. X represents displacement, vi represents initial velocity, vf represents final velocity, a represents acceleration, and t represents time. The next equation to prove is that the displacement an object travels is equal to its initial velocity times time plus 1/2 times acceleration times time squared. To prove this, let's look at the velocity time graph of an object which accelerates from an initial velocity of vi to a final velocity of vf during a time t. The area underneath the graph will represent the displacement of the object. So if we can show that the area is indeed vit plus 1/2 at squared, then we can prove the equation. First, let's split this area into a rectangle and a triangle. The rectangle has a height of vi and a width of t, so its area is vit. The triangle has a base of t and a height of vf minus vi. But recall from the first equation that vf minus vi is equal to at, so the triangle's height is at, which means that its area is 1/2 times t times at, which is 1/2 at squared. Now if you add the areas of the rectangle and the triangle, then you get vit plus 1/2 at squared, so we have proved the equation. The next equation, x equals to vft minus 1/2 at squared, can be proved using the same graph. Instead of adding the area of this rectangle and triangle, let's draw a larger rectangle than what we need and subtract the triangle which represents the overcounted area. This rectangle has a width of t and a height of vf, so its area is vft. And the triangle has the same area as the one before. It has a base of t and a height of vf minus vi, which is at. So its area is also 1/2 at squared. Therefore, the displacement, which is the area, can be represented as vft minus 1/2 at squared. We have proved the equation again. The next equation, x equals to vi plus vf divided by 2 times t, can also be proved using the same graph. Let's draw an imaginary horizontal line at the average of the initial and final velocity. You can intuitively tell that this line will cross the velocity function at a time of t over 2. Now, compare this trapezoid, which represents displacement, to the rectangle that's created from this imaginary horizontal line. To the left of t over 2, the trapezoid is missing a triangle that the rectangle contains. And to the right of t over 2, the trapezoid protrudes above the rectangle by a triangle. These two triangles have the same base, t over 2, and the same height, vf minus vi over 2. So the protruding triangle exactly fills in the area of the missing triangle, which means that the area of the trapezoid is equal to the area of the rectangle. The rectangle has a height of vf plus vi divided by 2 and a width of t, so the area is going to be the following. And therefore we have proved the equation. There's one equation left, and we can derive it by combining the 2 equations that we already have. From the first equation, vf equals to vi plus at. Solving for time gets us t equals to vf minus vi over a. Then we substitute in this expression for time into the average velocity equation, which gets us x equals to vi plus vf divided by 2 times vf minus vi divided by a. Then the numerator is vf plus vi times vf minus vi, which is a difference of squares, which gets you vf squared minus vi squared. So we get x is equal to vf squared minus vi squared divided by 2a. Then by multiplying 2a on each side, you get vf squared equals to vi squared plus 2ax. We're going to start solving problems soon, but let's first analyze these 5 equations a bit more. First of all, you can only apply the 5 equations given that acceleration is constant in the problem. Why? Because all of the proofs we've done for the equations relied on the fact that the velocity is linearly increasing. That is a straight line on the velocity time graph. A straight line on the velocity time graph graph means a constant slope, and a constant slope means a constant acceleration. So the moment acceleration isn't constant, all of the equations that we have derived do not work. So remember, acceleration has to be constant for you to apply the 5 kinematic equations. The second thing you should know is that each equation contains exactly 4 of the 5 variables. And this is important because it means that by knowing 3 variables, we can solve for an unknown 4th. However, you must choose the right equation, because if you don't, you might not be able to solve the problem. If a problem gives you the initial velocity, acceleration, and displacement and asks you for the final velocity, then the only equation you can use is vf squared equals to vi squared plus 2ax. This allows you to plug in the known values and find the unknown value for displacement. If you choose a different equation, like vf equals to vi plus at, then after you plug in the values, you can only find for the time, not the displacement. And so it's incredibly important that you choose the right equation. But how do you do that? Here's the strategy. Write the variables you know. Write the variables you're trying to find for. Then find an equation that contains all of those variables. That's it. To illustrate this, let's solve a problem together. I want you to pause the video, read it, then listen to my explanation. Now let's apply the strategy. First, write the variables you know. We know that the car starts at an initial velocity of 30 meters per second. We know that it comes to rest, so the final velocity is 0 meters per second. The acceleration is negative 6 meters per second squared. Write the variable we're trying to find. It's displacement. Third, find the equation that contains all the 4 variables that we have written down. And that is going to be vf squared equals to vi squared plus 2ax. Lastly, we plug in all the known variables and find for the unknown one. If we do that and solve all the algebra, we get a displacement of 75 meters. Try this problem yourself. Let's apply the strategy now. First, we write all the variables we know. We know the initial velocity, the acceleration, and the time. And we're looking for the position. We already know the initial position, and the final position is equal to the initial position plus the displacement. So the final position is technically the displacement. So the unknown variable we can say is the displacement. Now we find the equation that contains all of the 4 variables here. What is it? It's going to be this one. So we plug in all the known variables and find for displacement, which comes out as 36. So the final position is going to be the initial position, which is 0, plus 36, which is equal to 36 meters. For the first problem, we know the initial velocity, acceleration, and time, and we want to know the final velocity. The equation that has all these 4 variables is vf equals to vi plus at. Plugging in all the known variables and doing the algebra, we get that the final velocity is 24 meters per second. For the second problem, we know the initial velocity, final velocity, and time, and we're looking for displacement. The equation that contains all these 4 variables is this one. So we plug in the known values and we get 256 meters. Let's try trick gear problems now. For part A, look at phase 1. We're given the initial velocity because it starts from rest and the acceleration and the time. We're trying to find for the final velocity. The equation that includes all the 4 variables is this one. We plug the values in and we get 20 meters per second. For part B, we have to find the displacement for each phase separately, then add them together. For phase 1, we know the initial velocity, acceleration, and time. We're trying to find for the displacement, so we use this equation. And plugging in the values, we get 50 meters. For phase 2, we know the initial velocity, the final velocity, and acceleration. We're trying to find for the displacement, so we use this equation. And plugging in the values, we get 40 meters. So adding 50 and 40, we get 90 meters. For part C, we have to add the duration of each phase. We know that phase 1 took 5 seconds, so we just have to add the duration of phase 2. Well, how do we find that? We know the initial velocity, final velocity, and acceleration, and we're trying to find for time, so we use this equation. Plug the values in, and we get 4 seconds. So the total time is 5 plus 4, which is 9 seconds. Let's try one last problem and call it a day. For part A, during the driver's reaction time, the car is not slowing down, so it has a constant velocity of 30 meters per second. And it does that for 1 second, which means that it will cover 30 meters. To solve for part B, let's first interpret what minimum braking deceleration means. In this context, minimum braking deceleration means that the car has just enough deceleration to stop immediately before it hits the barrier. What does this mean? Well, we know that the car has already traveled 30 meters while the driver is trying to react, so it means that it will brake along that remaining 75 meters. So the 75 meters will be the displacement for this phase. So we know the initial velocity, 30 meters per second, the final velocity, 0, because the car stops, and the displacement, 75 meters. We're trying to look for the acceleration, so we choose this equation. And plugging in all the values, we get 6 meters per second squared. For part C, we have to add the time it took for the driver to react and for him to decelerate and come to a stop. We know the initial velocity and the final velocity and the acceleration for phase 2 when he's starting to slow down, so we use this equation to find for the time. And that gets us 5 seconds, and adding 1 second of reaction time, we get 6 seconds. Alright, that's it for 5 kinematic equations. As always, the practice problems and notes are on penguinprep.com with the link in the description below, and I'll see you in 1.3.